Recording. Okay. So good morning, everyone. I'm very happy to invite one of my best friends, Dr. Fangning Zheng, who is currently working as a computational geoscientist at Zanskar. And before joining the Zanskar, she conducted very exciting research, especially about the CO2 storage at the Los Alamos National Laboratory over 1 year. And she also holds a PhD degree in Petroleum Engineering at the University of Southern California. And today she's bringing us a very exciting topic about the deep learning assisted multi-objective optimization of CO2 storage. Fangling, thank you for accepting the invitation, and it's your turn. Thank you.
Thank you, y'all. Hey, everyone. Welcome to my presentation. I hope everyone can hear me good and hope you can see my slides. This is a good presentation view, right?
Yeah, I can see it clearly. Yeah.
Okay, thank you. So my topic today is deep learning assisted multi-objective optimization of geological CO2 storage performance under geomechanical risks. And yeah, as you can see from the topic, there are basically, I would say, 4 different topics in one slide. We'll be touching more on the CO2 storage, incorporating geomechanics for the physics-based simulation, as well as the deep learning-based simulation. And I will also talk about my optimization framework to optimize the CO2 performance under geomechanics. So let's get started. Here's an outline of my today's presentation. I will first talk about the motivation of my work, where I'll be interested in geomechanics and what's the challenges. Then I will give you an introduction about our problem statement and some definitions of the terms we used. Next, I'll talk about the methodologies of the work, especially about the optimization workflow and deep learning-based proxy model, then show some results and findings. So you know that geologic CO2 storage is a technology to store CO2 underground to mitigate the atmospheric CO2 accumulation. There are a lot of challenges when storing CO2 underground. For example, you need to calculate cost and benefits. There are safety issues. We need to perform risk management during the injection of CO2. And there are regulations when operating and etc. So today I'll focus on the risk management side, especially in rock deformation, induced seismicity, and CO2 leakage. These are closely related to the subsurface fluid flow problems, and in the next couple of slides, I'll give a detailed description of how I tackle this research. So why do we want to access the risk management? Here is a motivation example of a CO2 storage project called Insala project. People were doing a pilot test on the Insala fields to inject and store CO2 underground at this depleted oil field. While people are injecting almost 4 megatons of CO2, they detected a lot of seismic events. Over 9,000 microseismic events happened after the injection starts, which is indicated by the figure on the top right here. And not only that, people also observe a maximum of 25 millimeters of uplifting occurred at injection sites during the 2 years of injection, like what is shown here on the bottom right. Those are all because people were not properly accounting for geomechanical risks during CO2 injection. So to further investigate the effect of injection on geomechanical response, I designed a numerical experiment, a very toy problem of 5 injection wells for 15 years of CO2 injection into this saline reservoir on a different injection rate. And this diagram on this graph is plotting geomechanical risks versus injection rate. The red line is CO2 storage. The blue and green lines are the corresponding geomechanical risk represented by ground uplifting and rocks plastic deformation, which I'll give you a better definition later. We could observe that as we inject more CO2 into the reservoir, the greater displacement and plastic deformation the field will undergo, which means a higher potential for the reservoir rocks to undergo failure or fracturing. So this becomes two conflicting objectives. Our goal is to increase the CO2 storage while minimizing the geomechanical risk it will bring to the reservoir by finding the best combinations of injection location and injection rate in the field. So here comes the research objective. We want to optimize geologic CO2 storage efficiency under geomechanical risks. When we're injecting CO2 underground, pressure will build up and will induce some stress and strain changes in and around the reservoir to cause ground deformations and uplifting, rocks, plastic deformation, and potential microseismic events, as well as caprock fracturing and CO2 leakage. Those unwanted inelastic changes could reduce CO2 storage efficiency and cause concerns in local community. In fact, these types of geomechanical responses have been observed at many CO2 storage sites. So in the next three slides, I will show you how do we quantify those three geomechanical risk terms to be used in the optimization formulation. The first term of risk is ground uplifting caused by injection of CO2. This diagram on your right shows the vertical displacement field after CO2 injection. If we put the plane and get cross-sectional plot here, we could observe that the maximum vertical displacement is happen at the injection well location. And we use the maximum vertical displacement inside a field as one of the objectives to be minimized, which is represented as UZ here. And the second term is a little bit complicated, but I'm sure you guys from the geomechanical community are familiar with this term. It's called the rocks, it's related to rocks failure. So when we're injecting CO2 into reservoir rocks, they can either experience a volumetric expansion or shear deformation. And this leads to changes in the stress state of the rock following this path over here, which can eventually bring it to a point where it fails and undergoes permanent deformation. To model this plastic deformation, the Mold-Coulomb's failure criterion is used. I'll skip the details of the mechanism, but the high-level idea is that once the stress state touches the failure line, which is intrinsic property of the rock, the rock will then undergo plastic deformation, which means it cannot return to its original state even if we stop injecting CO2. And the maximum plastic strain represented by the maximum epsilon p here is used as another objective in the optimization formulation to be minimized. And this term is very important in quantifying the geomechanical risk during CO2 storage because it's highly related to the calculation of microseismicity. We are also concerned with maintaining the caprock integrity during CO2 injection and want to avoid any CO2 leakage caused by pressure buildup that could result in caprock fracturing. To address this, I developed a new leakage risk metric that I aim to minimize. This leakage metric shown here consists of two parts. The first part is the leakage potential before any actual leakage occurs. It measures how close the current stress state is to the point where stress exceeds the fracture opening stress. To model this, we use modified Bartolomeu's model. And the second part of the leakage metric is pretty intuitive. It's the total amount of CO2 that would leak out to caprock or an upper aquifer in the event of a fracture. If no leakage occurs, this term is zero. But if a fracture does occur, this term becomes a very large number, which I'll use to, pretty much I added here to be used as a penalty to the objective function, so to discourage any leakage. So moving on to the methodology part, I think I will give you an intro of the methodologies, including a general optimization framework that I developed and touch a little about the geological uncertainties. After this, I'll move to the data scientist part about building a proxy model that I developed for CO2 storage. So In this slide, I will introduce a general simulation and optimization workflow based on the problem we just defined. I first built a coupled simulation model using commercial software CMG. The model couples flow geomechanics and fracturing mechanism all together to account for CO2 storage amount and geomechanical risk that we just quantified. Next, oops, accidentally pressing the wrong button. So next, I formulate the optimization problem as to minimize the CO2 leakage metric through caprock fracturing by adjusting the well injection rates as the control variables. So in this case, the well locations are fixed and we can use gradient-based optimizer to perform the optimization and get multiple local solutions. And then among those local solutions, we choose a desirable solution under high-level criteria. I can also define the problem as to both maximize CO2 while minimizing the geomechanical risks, such as ground uplifting and rock failure, represented by these equations here, by looking for a better injection location. So the optimization variables then become well location, and we need to use global optimizer, such as genetic algorithm here to solve for the optimization. And we'll get multiple trade-off solutions as objective 1 is trying to maximize storage and objective 2 is trying to minimize the geomechanical risks. And then again, under high-level criteria, we'll choose a final desirable solution. The porous media for CO2 storage, like a saline aquifer, usually possess great extent of geological uncertainty due to the lack of understanding and measurement of the geological formations. We could also account for those geological uncertainty by acquiring hard data, such as well log data, and soft data, such as seismic profiling data, with a variogram model, and by using some statistic technology, such as kriging or sequential Gaussian simulation, we could generate different realizations of geologic properties, such as permeability or porosity maps. And when we're running simulations, we'll use all these realizations for running the model and take an average over the ensemble to statistically average out the uncertainties. So with all this, this is just an example of one of my optimization results, which I'll show you later. With all this, I will show you the numerical experiments part with well placement optimization, control optimization, and robust optimization result. So let's first tackle in the well placement optimization problem. This slide shows a simulation model I built in CMG to be used in the optimization. I use CMG gem to build this dual grid system with reservoir in the middle surrounded by overburden, underburden, and side burdens. You can see that this is pretty much the heterogeneous part of the reservoir where we define it as an injection reservoir. So I defined 4 lithal phases within the heterogeneous region, and the properties for each phases are listed and plotted in the slide here. We define the optimization problem as a multi-objective optimization problem. We perform as you can see that here we're trying to find the best well location W to minimize to actually maximize the CO2 total CO2 storage represented by MCO2 here. Minimize the negative means maximize it. And then the second objective is pretty much to minimize the maximum vertical displacement in the field. The third objective is to minimize, again, the maximum plastic deformation during CO2 or after CO2 injection over the field over time. So we perform a fixed BHP injection for 20 years and 4 wells to find the best well configuration to give us the most CO2 storage and the least geomechanical risks. And this slide shows a multi-objective optimization result. Since we have 3 objectives, so the solution space is going to be in a 3D space. As you can see from here, we have these 3 objectives being plotted on our solution space. And so So each black dot or red dot here is representing a simulation result with a specific well configurations. The red points are the Pareto front, where the solutions are at the boundary of the solution space and represent the optimal solutions. From the plot, we observe that for simulations with different well configurations. So here, pretty much this is a 2D projection of the 3D view of our objective of our solution space. So from the plot, we observe that for simulations with different well configurations, when total CO2 amount is the same, the effective plastic strain level can be very different. And similarly, when different well configurations are used with the same level of effective plastic strain, the total CO2 amount can also be different. Optimization can search within different well configurations with the same level of geomechanical risk and identify the solution with highest storage capacity. What I mean here is that, like, imagine you draw a vertical line here. What we're looking for is that so at the same level of CO2 storage, basically along this line, you can find the minimum value of the maximum effective plastic strain. And those red point is pretty much representing the optimal solution along the lines that you are drawing vertically over here. Those points are on the boundary representing that this value is being minimized. So we just identify the red point as our optimal solution. It can also search within well configuration with the same level of storage to identify those solutions that minimize the geomechanical risk. So same thing can be happen over the plot C over here. That's if you imagine that you're drawing multiple vertical lines here, and then those points on the boundary, like represented by the red dots, are giving you the minimum value of the maximum vertical displacement, which is identified as our best solutions. So yeah, this is pretty much the optimization result of our 3-objective optimization. Next, I'll just give you like a high level idea of how the well control optimization is being performed to minimize our caprock fracturing using the objective function that I described previously. So for the control optimization problem, I use the leakage metric I defined earlier as the objective function subject to a fixed amount of total injection rate. I then build this numerical simulation model in CMG again for dual grid system with injection reservoir grid in the middle, which is shown by this colorful rectangular shape here. And then we have also the underburden and side burdens to represent a larger geomechanical field. So we have a heterogeneous permeability field again in the middle of the reservoir domain to accommodate for 3 wells injection. They have a fixed location and injecting CO2 for 15 years. So this slide here shows the control optimization result. I first performed about 2,000 simulations with different control schedules to construct a solution space for the problem. And as you can see from the right plot here, this is a pretty rich plot, but the yellow region is, so basically these colorful surface, representing by these, yellow region and green and blue region, this is our entire solution space where I ran about 2,000 simulations to just construct this solution space. And then what you can see here, so basically this is our objective function. And if we have a leakage happen, this term will be activated and goes to a very large value. And this value is pretty much represented by the yellow region. on the solution space here. As you can see, it's having a very large log 10 numbers. So pretty much the yellow region is representing the leakage region. If your optimization solution ended up in the leakage region, which means that you basically didn't find a very good solution to minimize the leakage, right? And then this region, I define it as a safe region, is because it's having a negative log 10 values. This is pretty much meaning that the simulation didn't trigger the leakage term. So this large term is not there, and we are only like calculating this negative number term, which is why you're seeing negative values in this region. So this is what I define as a safe region. Basically, I performed two different optimizations with different initializations, which is starting, as you can see, from here and here. I hope you can see my mouse. But and then the lines shown here is a optimization trajectory. So pretty much we're starting from the boxed cross dot here, and then the next point is pretty much the next iteration of the optimization. And you can see that when we are starting the initializing the optimization from this point, at the next iteration, it just finds a safe region with to a point where CO2 leakage is not happening. And pretty much it's kind of trapped in this local minimum here. But then with another initialization, like for example, starting from this point here, it goes through several iterations still on the leakage region, but then it finally finds to the safe region and then find a very good point inside the safe region as the final solution. So what I wanted to point out here is that so from this surface plot of the objective function, we could observe that the solution space is pretty nonlinear, non-convex, and multi-physical. And there exists many local minima, which shows the complexity of this optimization problem. And we performed the optimization with these two different initializations, and they all converged from the leakage region to the safe zero leakage region. So let me show you an example of the optimal result that I obtained from this proposed optimization process. As you can see, the initial, so this is my initial setting of the well control with plotting the initial gas plume, and this is my optimal gas plume with optimized control schedules of these three wells. So as you can see, the initial gas plume has been redistributed. So this is pretty much the blue plumes are showing the leakage that's happening at well 1. And then after optimization, you can see that the gas plume from well 1 is being shifted to well 3, which means that well 3 is, and you can see that well 3 is located at a higher permeability region, which means that it has more space to accommodate for CO2 gas to minimize the ground displacement and caprock fracturing and etc. Which means that so we shifted some of the injection from well 1 to well 3 in order to avoid caprock fracturing that could occur if we inject too much gas into well 1. And one interesting thing I observed here is that well 3 ended up storing the most CO2 among the 3 wells. And this is again because it's located in a higher permeability region, which means that it's better at dissipating pressure during injection. As a result, the stress field has less changes, which could avoid caprock fracturing. So next, let's move to the robust optimization under geological uncertainty. Again, we use the same objective function here that counts for geological uncertainties. I use the average over ensemble to to be defined as the objective function for this robust optimization problem. I used the same simulation model with 100 permeability realizations to represent the geological uncertainty. And here are just plotting the mean and variance of the permeability map over the ensemble that is shown here. And this slide shows a cumulative density function of the robust optimization result. And as you can see from this left plot here, the dark blue curve is showing the CDF of the initial ensemble. And you can see that the log time value of it being minimized to a minus region, which is the red curve over here, showing that the majority of the ensemble, which is originally fall at a very large value, indicating rock fracturing, is minimized by the optimization to a safe region with zero caprock fracturing and CO2 leakage. And this plot on the right is showing just like a zoom in plot of the optimized CDF. And you can see that the entire ensemble is pretty much within the negative value region, indicating that all the ensemble is having zero leakage. So this diagram on the bottom shows the line plots of the initial ensemble represented by the blue lines, blue curves here, and the initial ensemble represented by the black and gray curves here, and the optimal ensemble represented by the blue and cyan lines here. This is plotting the pressure over time, as well as minimal stress over time and the total leakage over time for these strip plots. And you can see that the ensemble of pressure is being minimized from the black curves to the blue curves, and the corresponding effective stress is being maximized to a safer value. And also the total CO2 leakage is also being minimized from a large value to almost zero from the initial to the optimal ensembles. So this is pretty much the result of our robust optimization. Now there is one issue of the optimization workflow that I haven't mentioned about, which is the runtime issue. So the reservoir simulation requires some time to run, and especially for the coupled flow and geomechanical simulation. They're very computationally expensive since the geomechanics part is added, and usually it requires high resolution for the mesh grid. And all of that adding up to give a costly runtime. In my own model, it requires about 2 hours to finish a single run. Moreover, when we are performing optimization, usually it requires more than thousands of simulation runs to be evaluated to get to the optimal solution. And what even worse is that when geological uncertainty is considered in a whole workflow, 100 times or even 1,000 times more simulations are required. So this comes to a conclusion that optimization is too computationally demanding, and it's almost impractical to run in reality, even with the help of parallel running. So to be able to reduce the computational cost in a large extent, we develop a deep learning accelerated optimization workflow under geomechanics for CO2 storage. So for the entire workflow, the first step is, again, to build a physics-based model and use this model to generate training data with different control variables or location variables. Next, we built a proxy model based on that. Here we developed a Fourier neural network-based model, and the input contains permeability, porosity, well location, and control. The outputs include vertical displacement and plastic strain, which were defined in the previous slides. So based on this model, we define optimization problem, like I talked about in the previous slide here. In the results, I pretty much will be showing you the optimization result based on these objective function. It's gonna be a multi-objective optimization again, but when performing this optimization, we'll be using the proxy model that we developed for performing the forward simulation. So again, we want to maximize CO2 storage and minimize the vertical displacement and the effective plastic strain. safety factor is just like in the other side of the plastic strain. It measures how close the current stress state is to the failure point. So if the safety factor is a very small number, it means that it's closer to the failure point. And when the safety factor becomes 0, the rock will encounter rock failure with permanent deformation. So that's why we want to maximize the safety factor to make sure that it's being retained to a large value to avoid permanent deformation. So after we define our objective function and decision variables, we'll select the optimization algorithm. Since here we define it as a multi-objective optimization, so we still use genetic algorithm to perform this optimization problem. And then after we performing the optimization, we'll acquire optimal result, just like what we did before. So this slide is also a rich slide that it shows the results of our optimization. Result of our optimization also shows the surrogate model performance. So if we look at the left plot here, what you're seeing here is the 3D vertical displacement field as an output from the proxy model under 4 different controls. And you can see that the first row of each case is the 3D vertical displacement generated from a surrogate model. And the second row is showing the displacement from a physics-based simulation, which is the ground truth here. And you can see that the mismatch of each case is very small, indicating a superior performance of my surrogate model. And on the right, you can see that the genetic optimization result for this problem. Again, here I'm showing the Pareto front as indicated in these 3 2D projection plots. On the plot, you can see that we successfully bring up the safety factor from 0 as initial to a very large value to avoid plastic deformation during injection. And we also decrease the vertical displacement from the initial point to the Pareto front by about 25%. So this slide shows a computational cost comparison between the deep learning accelerated workflow versus physics-based workflow. If we use genetic algorithm convergence at generation 55 as a benchmark, we can see that the total number of simulation evaluated is about 1,650. So pretty much we need to evaluate this number of simulation to be able to let the genetic algorithm to converge to a very good solution. And performing this number of simulation for a physics-based model, it takes about 3,300 hours. But then for our deep learning-based workflow, it only takes about less than 30 minutes to perform the entire optimization workflow. So it's about 7,000 times faster, and this is indicating the effectiveness of the surrogate modeling based optimization workflow for tackling the CO2 storage problem. And yeah, this is pretty much the end of my talk. Thank you for your time, and please feel free to ask any question. I hope this presentation, I know that it's pretty much based on a very high level explanation within this 40 minutes, but I hope it's making sense to everyone, and please feel free to ask any questions. Thank you.
Thank you, Fangning. Any questions from the audience? You can either type in the chat or just speak.
Yeah. May I ask a question?
Sure.
Okay, great. Yeah, this is Bill Harbert from Pittsburgh. This was really an outstanding talk. It's just incredible. I had a couple of questions from the beginning. The thing that I found fascinating was your and very thorough, and thank you for including a description of the space that you were determining an optimum solution within. That was incredible, fantastic. In terms of that, you're now at the point where you can, with respect to spatial analysis, quantify where these risks are located because you're doing initially a full physics simulation, or with your optimized reduced physics approach, again, a very thorough analysis of specific leakage metrics. And although this doesn't necessarily relate to your talk, and I apologize, it's a little out of field, but have you thought about categorizing your site overall with respect to where these major risks are located with respect to the area of safe storage? And if you'd like to pass on that, feel free, but thank you for an outstanding talk. This I've learned a huge amount.
Thank you so much, Dr. Halbert. So for the location of the risk, that usually like the maximum risk, either defined by the vertical displacement here or the plastic deformation. It's for the vertical displacement, it's probably more intuitive or less nonlinear, is that the location of the maximum displacement is always happening at the injection point. That's our observation. But then for the plastic deformation, it's another story. So in one of our paper, I think it's my first journal paper, we were having this observation showing that the maximum plastic strain that can happen during injection, it doesn't necessarily to be located at injection point, but it might be located if we have multiple wells. The highest potential for it to occur is usually between each wells, because I think that's naturally due to the method for calculating it. It's we're using more coulombs to quantify this quantity, and basically the shear. So when you have multiple wells, the gas plumes the injection stress field changes are affecting each other. So the shear stress it will always be larger than the volumetric expansion or contraction. So when shear stress happens and it's larger, usually the highest plastic strain deformation is happening between wells. And that's our observations for plastic deformation. And then for the third term that I defined for the leakage term, this term is pretty intuitive because we're basically just calculating the minimum stress, to versus the fracturing opening stress, as well as the leakage amount. And this is pretty much always happening around the injection location. It's pretty close to the injection location, but this term will always be happening in a caprock, because we are only quantifying for the caprock's fracturing. So we basically only calculate the rock fracturing inside a caprock. So this term will be inside a caprock, but usually it's just above the injection point. Does that make sense?
Absolutely fantastic. And at this point, you can fully forward replicate and model everything that happened in Insula with respect to observed microseismicity. It's just incredible, the insights in your model. Thank you.
Thank you very much.
Any other questions from the audience? Okay. Yeah, Fangning, I have a question. Is just for curiosity. So your current surrogate model and I know your current and past research are focusing on the CO2 storage. And do you think all these methodologies, including this optimization and surrogate model, can be further apply to the hydrogen storage? I mean, if it can, what will be the challenge and the difference?
Oh yeah, definitely. So right now, I'm still um you know, although I went to industry, but I still want to like staying in the research part. So I'm still doing a research with my previous professor at USC. So right now we are investigating a very interesting topic. It's ongoing. It's more about a faulting system near for hydrogen injection. So basically we're exploring how to when the faulting system is changing, like for example, if the strike and dip angle is changing, how will a hydrogen storage field nearby being affected? So that part is we are still focusing on building the physics model right now with different settings of the fault systems. But eventually we want to perform optimization and we also want to build a proxy model based on that. But it's going to be a very difficult problem because with adding the fault, you're adding a lot of nonlinearity into the problem. So it's going to not be a very easy proxy model to build, especially, faulting system is having a very different grading than a normal reservoir simulation without the fault. So that part it's ongoing study. Right now we still building the physics simulation, but the next step is to think about how to build a physics informed deep learning model with the system. And then after we have done with the proxy model, the next step will be basically implement the optimization workflow into using the proxy model of the faulting system. So I think in hydrogen storage, this whole workflow can also be useful because it's basically like if you can build your physics model and based on your physics model, develop a proxy model, then this whole workflow can be applied no matter how you might define your objective function differently, but it still can be applied to not only even hydrogen storage, even a geothermal system or other subsurface dynamic system can use this workflow to perform the optimization that the user is interested.
Yeah, that's very interesting and sounds very very exciting. And it sounds like to me if the problem has existing, you talk about fault, but I mean for me it's like fractures, right? I mean if there is existing fractures, which means the discontinuity of the problem of the domain, it will raise the question about it will raise a challenge to build a deep learning model, or will that like affect the further computational cost about the training?
Yeah. It's definitely gonna. I think you're mentioning that these 2 points are pretty valuable. Yes, both will play an effect. So what I'm observing is that for CO2 storage model without a large fracturing system, usually for my simulation, I can reduce the runtime to like within an hour or 2 hours. But then if the fault system, like a large fault system is added, my simulation suddenly goes to 24 hours. So this is gonna be a bottleneck.
Really affects a lot.
Yes,
that surprised me. That surprised me a bit. Yeah.
Yes, because the discontinuity is just too much, and too many nonlinear calculations happening. And that's one of the bottleneck. The other bottleneck is how are you going to construct this kind of proxy model involving faulting system? So I think that really depending on your grading structure. Right now we're still using CMG, so it has to be a structured grading, structured mesh system. So it's relatively easier to be implemented into the deep learning structure, just because you have a structured system, structured grid, right? So what CMG does is that you have to construct a very thin
Mesh.
grid mesh grid to represent the fault, but anything else you can treat them as a regular like a grid block in the system. So I think the gridding part is should be easy to tackle. But right now we're still thinking of how can we add the physics involved methodology into the deep learning network.
Yeah.
We haven't think of it yet, but I think that's gonna be another bottleneck.
Yeah, I think
So
that's a good thing to
yeah.
think. Yeah.
Yeah.
Yeah,
Thank you for
thank
mentioning.
you. And dear Fangning, can check out the chat. Like, yeah, Brant has questions.
Okay, so thank you. The question is, was the thermal stress included in the geomechanical? So for this, it's not included. We are using isothermal system, but in the future we are, if we're dealing with a geothermal system, I think we'll be incorporating the thermal effect into it. And the second question, any discontinuity in the model? Yes, there is a lot of discontinuity. So by discontinuity, are you mean discontinuity in the grading system, or can you better define the discontinuity? Like, for example, are you looking at, am I using the discontinuum method versus continuum method? Oh, okay. Thank you. Yeah, so the CMG run is on CPU. The deep learning structure is run on GPU. Thank you. All right. I think if we don't have any further questions, maybe
Okay.
we could let.
So thank you again for Fangning to delivering this very, very exciting talk. And I would like to also to announce that we will have our next speaker delivering talk 2 weeks later. It should be June 19. And also thank you for the attendance for all the audience. Thank you. Have a nice rest of the day. Bye-bye.
Thank you. Bye.
Yeah, thank you. Have a great day, and thank you for hosting this. This was really awesome work. Great
Thank
work.
you. Also nice to see you,
Oh,
Dr.
yeah.
Howard.
Yep. Cheers. Bye.